Hi, welcome to Concept Based. I'm John Hepworth, and this is another one for Year 11 Extension students. Just before I get started, I'd like to apologize for the sound on the previous YouTube videos. Now I have sorted out what the problem was, a bit of a noob error, but as you can hear now, far more professional sounding video and hopefully much easier on your ear so you can listen to it a bit longer. All right, so Year 11 Extension, we should have moved on in the scope and sequence now away from inequalities. Been there for a few weeks. Where you go with your school will be different for a lot of students, but the recommended scope and sequence for Extension 1 students is now into polynomials. Now, with students going into polynomials, there's going to be two groups of students. One group of students that did a lot of the polynomials content in Year 10 and those that didn't. I'm going to assume that you have done polynomial content in Year 10 and not revise it in this video, but I will mention what it was that you were taught in the course back then. So in Year 10, polynomials path topic, there is a section that's called graph polynomials, and it says that you would have graphed quadratics, cubics, and quartics. Okay, so up to what's the word I'm looking for? The power of 4, the degree. That's what I'm looking for. Use the correct terminology. Up to degree 4 polynomials you were graphing there. It says here in your scope and sequence in the syllabus as well that you understand about the zeros and that you will take into consideration single, double, and triple roots of a polynomial. And so how that affects what's actually going on when you're graphing them. So that's something that I want to look at here today. Essentially graphing a polynomial. I've written a polynomial, as you can see in this question, as a factor of its linear factor, an expression as a product of its linear factors. There's two linear factors there and they have different degrees of those factors. So we're going to have a look and see what that does. We'll probably have a look as well at what we have to take into consideration with the leading coefficient with polynomials, and also take into consideration what's happening out towards infinity as these polynomials go out on the x-axis. So first of all, I'd like to mention that I love this topic because I want my students to be really good at graphing polynomials. I want them to be comfortable graphing things before they do algebra so that they can check their algebra skills and in the future their calculus skills by confirming it against a sketch that they've drawn. So we want to be able to draw polynomials of any degree really, and not be limited by simply being able to do essentially quadratics. Students are comfortable with parabolas, but even in cubics they can sometimes be challenged. So let's get into this one and let's go ahead and graph this polynomial. First of all, I want to talk about the leading coefficient. The leading coefficient is obviously very important in a polynomial because it certainly sets its overall shape. So if the leading polynomial of a leading coefficient of a polynomial is positive, what we'll always see is that the polynomial will end up generally going upwards in a positive direction in the end. Now this makes sense because the leading term has the highest power on it, and so say if it's degree 4, x to the 4, so any number raised to the power of 4, as that number gets bigger, it's going to get much bigger, and therefore the whole polynomial is going to be becoming very positive and moving up to the right. So we see if we have a positive leading coefficient, it's going to go up in this direction. Therefore, if we had a negative leading coefficient, we would expect the polynomial to go down in this direction. Now you might be thinking I should be also drawing what's going on the other side of the graph when you have a positive or a negative, but the truth is we don't know. Because what then depends is what degree the polynomial is. So in the Year 10 course, as I said, you did graph cubics, quartics, and hopefully you would have realized that if the polynomial has an odd degree, 1, 3, 5, 7, so on, then the polynomial is going to start in one section of the graph and it's going to end up in the opposite section. So let me explain that. So say we had a polynomial that was degree 1, the most basic polynomial is a linear function, right? X to the power of 1. That's just a line. Y equals mx plus b, or mx plus c now in your syllabus. That x is raised to the power of 1. So that's a degree, an odd degree. And if we graphed a line, we would expect to see the polynomial doing something like this. So as you can see, if it's a positive linear function, it goes up, but it's in the opposite down in the other direction. And this is what we see for odd. It will actually switch. But there are other kinds of lines. What if there was a line with a negative gradient that went like this? Well, once again, we see that it's ending down here, but it started up here. So this odd degree polynomial switched. It went from one side of the x-axis down to the other as it moved across. Whereas if the degree is even, now we've got some very normal even degree polynomials that you've worked with previously, and they were quadratics. So a quadratic starts with x squared. So if it starts with x squared, the degree is 2, and therefore the degree is even. Now, if I was to go and continue on this line that says positive up here as a quadratic, we would expect it to look something like this, where it ends on the same side of the, I should have said y-axis, sorry, on the same side of the y-axis here. It's both positive on both ends. And if it was a negative parabola, it would have started down here and gone down here again and gone negative. So it would stay on that same side again. Now, these are the most basic odd and even polynomials, but it actually holds true for any degree. So if we were going to step up and we went to a cubic, so a cubic, x to the power of 3, odd polynomial, then we would expect that cubic to come in from one side and end on the other side, on the opposite side. And that's because it's odd. So the odd ones go from one side to the other. And then if we step up to a quartic, an even one, so let's say a negative quartic, that could look like this, where again, it's an even degree quartic, x to the power of 4, so therefore it doesn't change sides. It stays on the same side of that y-axis as the function goes down to negative infinity or up to positive infinity. So this is the general shape of polynomials that we have to take into consideration. So what was the rules that we learnt there? If the polynomial was odd, it will switch sides. Okay, it'll go from one to the other side, one side to the other. If it's even, in the end, it will stay on the same side. It won't always stay, like it will cross the x-axis at its zeros, but it will stay on each side when we're talking about going off to infinity and negative infinity. Don't forget, the polynomial might be positive and going up to the right, or negative and going down to the right when it finishes. So with these two things into consideration, you can find a general shape of any polynomial before you go ahead and look at the zeros. Okay, so let's look at this question that we're doing. We've got x minus 1 to the power of 3 and x plus 2 to the power of 2. Now, if we did expand x minus 1 to the power of 3, which we wouldn't do because that's a lot of work and we're going to get a lot of terms and we could make a mistake, but we're going to take into consideration what the first term would be that would come out of that x minus 1 cubed. And the first term would be x cubed. In the linear x plus 2 squared term, if we squared that all out, the first term that would come out of there would be x squared. So we would have had x cubed plus a bunch of other terms, and then we're multiplying them by x squared and some other terms. And if we do x cubed times x squared, we're going to get x to the 5. So essentially we can see the degree of the polynomial just by looking at the powers in the linear functions, in the linear factors, and we can see whether it's going to be odd or even. We can also look and see whether it's going to be positive or negative. We can see the terms in here is going to give us a positive x, and in the other one is also going to give us a positive x, and a positive times a positive is going to give us some sort of positive x to the power x polynomial to degree 5. So we've got that information so far. It's positive, it's going to go up to the right. It's degree 5, so it's going to switch. All right, so we've got that information. we're going to try and go ahead and graph this. When we graph it, we obviously are going to take into consideration the zeros from these factors. So we now have a 0 at 1, null factor theorem, a 0 at -2. We know that the graph is positive, leading coefficient, so it's going up to the right. And we know that it's an even degree, 5, so it switches sides on the y-axis. So we've got this much information. Now, what happens in the middle can be very complex, and the higher degree polynomial you're dealing with, the more complex it will be. But then what we have to do is go in and use our zeros to help us understand what's going on. So let's look at what's going on at the zeros. The zeros can have a couple of options with what's called their multiplicity. If a 0 has multiplicity of an even amount, it's going to cause what I would say is a bounce. Now you're used to this from quadratics. So let's just take a quick side note. If you graphed a standard quadratic, y equals x squared, look, the factor is an even factor, x squared. You know, it's x plus 0, but we don't need to write the 0, x squared. And when we graph that, we see the thing bounce. When I say bounce, I mean it doesn't cross the x-axis, it hits it and goes back up. But when we had factors with an odd multiplicity, so in this case 1, we're used to seeing these ones go through. Okay, so the options are through or bounce. So again, you could take that as some notes. If you have multiplicity of odd on a factor, it is going to go through. And if you have an even, it is going to bounce. Now it will always bounce back to the same side as where it's coming from. And obviously when it goes through, it's always going through from that side. So let's have a look. We've now got a multiplicity 3 on this linear factor. Therefore, if it's odd, like our x to the power of 1, which is our lines go through, so odd goes through. So we're expecting this x at 1, the x minus 1 factor here, we're expecting it to go through. Over here at this one, we've got an even multiplicity, so we're going to expect a bounce. So what we have to look at and go, well, where is the graph coming in towards this factor? Well, it's coming in from the bottom here, so we're expecting it to bounce and stay on the bottom. Let's look at where it's going to join up over here. That is also on the bottom, so we're happy with this. We're expecting this bounce to come along and go like this. Just touch the x-axis and then bounce back. Then come to this one and go through. Now it can be a little bit more complex than just go through. There are ways in which graphs can go through that look a little different. You can go through like this, as opposed to going through like this. So you can have a little bit more complexity to the polynomial as it has higher and higher degrees. And this one is a triple, so we actually would start to expect to see some curvature like this. Now, this is concept-based. I love talking about concepts. So I'd want to talk about this specific case right here as, well, why does it do that when it's got a power of 3 and it just sort of goes straight through when it's a power of 1? All right, let's have a think about that. We don't need a y-axis. If it just went straight through, when it's raised to the power of 1, it's not timesing itself. But let's think about the number 1. What if this is, say, y value 1 here? Everything in this part of the line here is less than 1. And if it has a multiplicity, in this case of, say, 3, if you multiply a number that's less than 1 by itself 3 times, so let's take 0.5 for an example. So say we were right here. 0.5 times 0.5 is 0.25. 0.25 times 0.5 is 0.125. It becomes significantly smaller and gets pulled down. Whereas if you had the number 1, 1 times 1 times 1 is just 1. If you have a 0, 0 times 0 times 0 is just 0. And so you end up changing it to having this bit where when it's below 1, that wasn't the best returning line, when it's below 1, it actually gets pulled down. And that same thing happens down here. That's why. But when it's above 1, anything above 1 raised to the power of 3 gets bigger than what it used to. And same when in this negative direction. That's why this curvature happens. So we need to take that into consideration when we're looking at our little straight through here. It's not actually going straight through when it has multiplicity 3. It's actually going to go through with a bit of a curve like this. Now, it doesn't have to be perfect. Markers aren't going to be wanting this absolutely perfect in the HSC, but they want you to demonstrate that you do have the understanding. So it doesn't have to be right, but it doesn't have to be perfect, but it does have to demonstrate that you understand that that's what the graph is doing at that point here. So let's just continue this one up in this positive direction. And now we're going to go down. And now if this one goes down and this one goes down, well, they must meet somewhere unless there's an asymptote between them. And in polynomials, straight up polynomials, there isn't. So we're going to join these two together. Now we have some information about this join. That was a terrible, terrible line of join. The information we have is we've crossed an axis. Look at this. We've crossed the y-axis. We should always be graphing that part of the polynomial. And what value is it? Well, in our first linear term, we have -1 times -1 times -1, which is -1. And in the last one, we have 2 times 2, which is 4. So this is actually crossing at -4. And then we're bouncing off here at -2 and coming down and going off in the negative direction for our polynomial. And we have a graph one thing we don't know it yet is just where the minimum part of this graph is, whether it's before the y-axis, after the y-axis. Some students like to think it's exactly in between the roots. It's not always, so don't assume that. And you're not going to get marked down for it not being in the perfect place at this point because you're not expected to find that minimum turning point. You might be given it in the question where, of course, you would then have to graph it. But if you're not given it, then you would find yourself in this situation here. So this is what we end up looking like. Now, this might seem like it's pretty rough and, that may not be the exact graph that we would expect. Well, how could we check that and make sure that our sketching is pretty good? We could go ahead and use Desmos. So let's go and chuck this into Desmos. Y equals x minus 1 cubed. Now here you see an example straight away in the graph that near the axes we have this twisting part. It's not just a straight line. It's what I was talking about that twisting part. X plus 2. So if you're not using Desmos regularly, I highly recommend it. It is fantastic for checking your solutions. And look at what we have here. Now, sure, my y-axis scale is a little bit off in terms of the other one the one that I've drawn. And obviously the graphing software is very, very smooth. But here you see it exactly a lot as the way we were graphing. Let's make this a little bigger, actually. We've got room here. So we see this bounce at -2 up here. We see it crossing at 4. Here's that minimum turning point that we haven't worked out yet. You will in the future using calculus, but we're not working that out yet. And then here, this bit here, I want to zoom in on. Here's this twisted through line. This is where it has a multiplicity of 3, and this is what we're expecting to see when we go through with that level of multiplicity. So there we go. It's pretty close. This is definitely enough for a HSC marker to be happy with what is being graphed here in terms of the information that's given and the shape that's given. This is the sort of thing they want to look for. In the HSC, you'll be expected to graph about the size of a third of an A4 page, a little bit more space than what I've got here when I graph. But in that third of a page, you'll really have that opportunity to demonstrate the real key features such as these zeros, how they go through the zeros, the direction of the top and the bottom of the polynomial, whether it's negative or whether it's positive. So hopefully you had an idea of what this polynomial might look like before we started it, and hopefully in the end you understand exactly where we are at when we get this polynomial to this point here. Once again, if this is the type of tutoring that you're after, understanding the concepts of questions and not just going ahead and doing some sort of procedure, following some sort of rule, but understanding why something is the rule, then feel free to reach out, info@concept-base.com.au.